All right. Good morning, physics. This is the first video of Unit 5, so congratulations. You've made it farther than most of my physics classes have throughout the entire year. Today, we're going to be talking about work. Now, work in physics is not the same as work in, for lack of a better term, reality. In reality, we would say that you've been doing work if you've been doing just about anything. You're expending effort, you're doing work. Physically, though, in order to be doing work, you have to meet a couple of criteria. And so that's part of what this will be over. And then after that, I'll show you some of the math behind that, which the math is pretty straightforward. So that said, let's get started. Okay, I should probably start off by pointing out that work is a scalar quantity, not a vector quantity. Okay, and that's because there is no direction. Work is not a directionally dependent quantity. You're either doing work or work is being done on you, which we'll talk a little bit about that, but not a whole lot. The units for work and energy, because they are the same, the units for work and energy are joules. And a joule is a Newton meter. Wow. A joule is named after a dude who did some really important work in thermodynamics. And that's actually where we first started using joules. And the farther we've gotten and the more we've learned about different kinds of energy, the more clear it has become that they're all related. So we named the unit for energy and work after this guy, and we'll talk about him in chapter 10, 11, or 12. I don't remember which. Probably 10, but we'll see. So a joule is a Newton times a meter. Or joule is a Newton meter. Now, this brings in one of the first times that we've had to talk about the difference between a dot product and a cross product. In physics, there's two kinds of products, dot and cross. Now, there are lots and lots and lots of really scientific differences between the two, and really important differences between the two that you do not need to know for this class. The main thing you need to know here is that a dot product is a product between two quantities that are acting either parallel or anti-parallel to each other. So they're either both in the same direction or they're in opposing directions. A cross product is going to be perpendicular. And we'll talk about cross products more in units or in chapters 7 and 8 when we do rotational systems. But work is our first real dot product. Now, the important thing here, work can only be done if the force and the distance are in, or the distance of travel, are in the same dimension. So, let me grab my book here. Actually, that one's not going to work, so I'm going to pause this and go find a better book. All right, so here's our book. This is the CRC, which you'll be using if you take Physics 2. So if we're going to do work on this book, then the force that is acting on the book and the force that is being overcome, the resistive force, and the distance traveled have to be in the same direction. So right now I'm holding this book. The only force that I am exerting on it to overcome is I'm exerting a force to resist the force of gravity, which is pulling it down. Okay, but I'm preventing it from falling down. So I'm not actually moving. There is no displacement taking place. So there is no actual work being done while I'm holding this. That said, I am expending effort to do it because I'm resisting the force of gravity. but I'm not overcoming the force of gravity. Now, if I raise the book, then I'm now moving at a distance in opposition to the force that's acting on it, gravity. If I lower the book, then I'm again expending effort to move the book, but this time in the same direction as the force that's working on it, or that's acting on it. So when I raise it, I am doing work in the book. I am taking effort and I'm putting energy into the book to increase its potential energy because I'm lifting it higher and higher. When I lower the book is doing work on me because it is losing energy. That energy has to be going somewhere. It's coming into me. I am gaining the energy that the book is losing. Now, I'm not gaining it as potential energy, or I'm not gaining it as gravitational potential energy, but I'm still gaining energy. Now, what if I move the book across the screen like this? If I move it sideways, I'm expending effort, but the distance that the book is moving from here to here is not in the same dimension as the force that's acting on it. The force is up and down, but the motion is horizontal. Since the force and the motion are not in the same dimension, no work is being done. Work is only done if the motion and the force are in the same dimension. Now, gravity is one of the main forces that we're going to be dealing with to actually do work. But there is another one that causes work a lot, and that is friction. Now, friction, unlike gravity, can be in multiple dimensions. Gravity is only ever going to be up and down. But friction, if you've ever tried to drag something heavy across the floor or move a heavy piece of furniture, you've experienced friction impeding your work your process. And that's because friction is doing work, or you are having to do work to overcome that friction. So in that case, friction would actually be friction would be causing work, or you overcoming that friction would be doing work. So that said, one more thing. Okay. Now the actual equation for work, which I haven't given you yet, you could probably figure it out based on the unit. But work, which we use an uppercase W for, which is why we did not use an uppercase W for weight. We used FG instead. Work is equal to the force that you are overcoming, or the force that is being applied, times the distance that you're traveling in that same dimension. So W is equal to F times S. So let's say that we want to do a calculation with this book. Okay, I would have to know the mass of the book so that I could calculate its weight. Okay, and then I can exert a force on it, F, to raise it. Okay, however, the force that I apply times the distance that I travel is equal to the work that's done. Now, this is where there's a little bit of overlap between chapters 4 and 5, because I can give you information to calculate the force without actually telling you what the force is. So if I tell you the mass, and I tell you how far it's gone, and how the different times that it took, then you could use kinematics to actually calculate the acceleration. With acceleration, you could calculate the force, and then with the distance traveled, you could figure out the work. So you'll have to keep an eye out for stuff like that on this. Now, for an actual practice problem, let's start with the very first problem in the chapter. So, page 153, problem 1. A weightlifter lifts a 350 Newton set of weights from ground level to a position over his head a vertical distance of 2 meters. How much work does the weightlifter do, assuming he moves the weights at a constant speed? So, if he's moving the weights at a constant speed, here's why that's important. If he's moving the weights at a constant speed, then the force he is exerting on the weights has to be equal to the weights, to the weight of the weights. So that it's telling us then that FA is equal to FG. So if these are, this is the barbell that he's lifting. If it's traveling at a constant speed, the only two forces acting on it are the force that he's applying to lift it and the gravitational force pulling it down. Can you actually see that? I just realized I grabbed a red marker instead of a dark marker. I don't think you guys can see that, so I'm going to redraw that. Doesn't look nearly as good the second time, but oh well. So we have his applied force going up and the weight of the weights, gravity pulling it down. So if we're traveling at a constant speed, that tells us that the acceleration is 0. So our sum of forces then would state that FA minus FG equals 0. Therefore, FA must be equal to FG. So the force that he's applying, which is the force that goes here in our equation, has to be equal to the weights. So we can just take that weight, 350. It tells us even that FG is 350 newtons. So we can just take 350 newtons times the distance that he moves them because he lifts them. That distance is going to be 2 meters. Is it 2 or 2.0? 2.0 up, so we've got our 3 digits. 2.00 meters. That's going to give us 700 joules of work done. And that's really it. Work is pretty straightforward. If you guys want, we can go through a couple more complicated problems, but that's it for this video. Work is not terribly complicated. It's one of the simpler things to really come to understand. So I hope this video helped. This video is probably posting a little late because I'm recording it Thursday morning. And it's supposed to post Thursday after school, but I've got to record another video for my chemistry classes after school. So this video can't post till I get home tonight. But I will get it posted tonight so that you've got it to look through. So that said, have a good night, and I will see you all in about 4 hours. 5 hours. It's 7. What time? Doesn't matter. I'll see y'all later. Have a good one.